Have Professor Wang back. He will continue his lecture on quantum extremal transitions.
Okay, thank you. You are still here. So last time I introduced this the notion of A plus B, a combined information in order to decide the information on the carnival transition from Y and to X. And this is a carnival transition. There are several ordinate double points. And you have the corresponding vanishing cycles, SI3. And you also have the corresponding extremal ray, that's SI2. I write this as CI. Yeah, and these are three spheres. And there are mu linearly independent vanishing cycles. And there are rho linearly independent rational curves. And it turns out we have this very beautiful Clemens relation of this, which just follows from simple topological calculation. And then I say we can upgrade this into Hodge theoretic version. So I call this basic Z sequence, which means you take H2 of Y divide by H2X. Then you go to CK, label these K points. And then you go to the, this is a vanishing cycle here, the space of vanishing cycles. So yeah, that's a span over all of these SI3. But it's mu dimensional. And more importantly, we know exactly the map here. So here, this is excess A model. And this is excess B. However, to get this map, what we use is the B matrix. And what we get here is the A matrix. In fact, we go this way, we take transpose. And what's the matrix AB? The A, here we are in the A side. I mean the A model on here. So the relation A is the relation matrix of this. And here we have the relation matrix. Let's B for this. Well, that's the interesting part. But you have to map this by B, and you have to map this back by A. Okay, so this is a Hodge theoretic diagram. But then something even better is you can upgrade this into a symptotic D module. So a D module upgrade. But only asymptotic, which means we can control the Ikawa blow up behavior. And to write down, last time I actually write down the 3-point function, either on this side or on this side. And you see from that expression, the information here was captured by A matrix coefficient. And the information here was captured by the B matrix coefficients. But you can, the way I write it down is because I really know what kind of connection I should put in the middle. So actually, we just put a very trivial one. Let's say dzi and zi sum I from 1 to k. And here, we just put the simplest possible trivial matrix, 0, 0, 0, 1. And that's for each piece, this means on each piece C, and you consider this bundle, you just take a 2 copy of it. Now let's say it's a dual of it in this way, and then this matrix acts on this bundle, and this is one of the reasons I think this might have some relation with this generalized geometry. So actually, because once you know this, so here you are also taking the double of this B, and you are also taking the double of this thing. And I still don't have a very good explanation for this upgrade. So the reason the thing is what I claim is you just pull back this totally trivial connection, the log connection, by these two maps. So you just do a restriction to here, then you get the dwarfing connection on these directions. And if you conversely, if you but now you have to take a dual to this CK. And if you pull back this connection from this side to here, then you get exactly the asymptotic of the equal coupling, the Gauss-Manning connection. So you see, this is really a asymptotic upgrade. But then I decide to show you the proof of this just later, because I think this is very interesting. And the proof really relies on what I said, this the extension of the nilpotent orbit theorem to the non-normal crossing situation. So it's non-normal crossing because what does this map means? This means you have a vector space, which is CK. But now, you take an orthogonal decomposition of this means you just take an orthogonal decomposition of this space into two parts. So you basically just take, for example, take a two-dimensional slice. So this is, let's say, k equals 3. And let's say this mu just equal, let's say, 2. And this V. So the embedding of V is in this. And then the orthogonal part is this excess A. So you get some vertical line there. And then what you see is then you get a two-dimensional, codimension 2 discrete locus in your Calabi-Yau moduli. So remember we draw the picture like this. This is moduli of X, and this is moduli of S bar. And in this case, the Bogomolov-Tiantodov theorem actually extends to conical. So we know the MS bar is actually smooth. So this is exactly containing it. It's basically identified. Yeah. And then we also know the modular space of Y is exactly contract as a boundary strata in the downstairs moduli. And this transversal direction is a codimension mu. So it's codimension 2 in this spatial picture. And then, so what does this tell us is locally, this just looks like, what's the neighborhood here? It just looks like a disk with mu-dimensional disk and times my. That's the moduli near S bar. And so you see, this in this example, this is a two-dimensional disk. But you have a k ordinary double points. So now you go back to think what's the information if you just look at this two-dimensional slice. Then it just becomes you have a two-dimensional vector space. But now you have three things intersect. Because you need to look at the three boundary, the axis hyperplane. And that's the degenerate locus for this. But the geometric realization becomes, I call this central hyperplane arrangement with axis AX. So we call this central hyperplane arrangement with axis my. Okay, so you can draw a picture like this, but it's impossible to draw the blackboard. The dimension is too low, so better not draw anything. But you really want to know, this thing has codimension 2. And the exceptional the discriminant locus has 3 pieces. So it's not normal crossing. Okay? But still, we want to do some analysis really in the locus. Okay? So that's the meaning of this basic sequence. Okay. Then before I show the detail, I want to emphasize what's the most important next step? What's the real challenge? The challenge is to make this sequence become something in D module, in real D module. Because this is just asymptotic. But I want to make this to be some, for example, if you look at this, you should have the Dubrovin connection. And then you really should get some differential equation over some compact curve or some compact base, just like in the previous talk. For example, you have a type 2 contraction, then you really get some ordinary differential equation defined on P1. And that P1 is basically the parameter of the extremal rate. Either you use the P coordinate or Q coordinate. Anyway, it's a P1. It's a modular curve. But in this picture, I didn't see that. I just get a very asymptotic behavior of this. And for here, I also just get a very asymptotic behavior of this. But if you really work on any Calabi-Yau moduli space, when we work on Calabi-Yau, all the models given are explicit. For example, toric or like other models. Then usually you already have the compactification base. You already have that family. So usually you already know how to write down the Gauss-Malin connection or the associated Picard-Fuchs equation of that. So the goal is really, why I show you in this picture is, if I know the information, the asymptotic information here, I already know the asymptotic information of here directly and vice versa. But we want to do something more. We want to say, if you know a better information, for example, the Picard-Fuchs equation, a Gauss-Malin system, can I really recover the quantum information here, not asymptotically, the complete information? So that means I want to make this diagram into maybe maybe need to enlarge this into a triangle in derived category of D module. But if you think in that way, actually I tried for more than 10 years and failed all the time. The reason is quantum cohomology is not D module. Although for one individual quantum cohomology is identified as a quantum D module after by Giventhal's theory of Lagrangian cone. But that's not really the definition of quantum cohomology. It has a lot of various descriptions. One description is Frobenius manifold. There are several different descriptions of it. But if you think about that, then you will realize this is not an exact sequence of D module. It's actually an isogonal splitting of Frobenius manifolds. It's actually telling you this is just a linearization along the degenerate boundary. And it seems that there are something very trivial. Let's say these are semi-simple Frobenius manifold. But then you have two highly non-trivial, semi-simple thing, but not semi-simple, the Frobenius manifold thing, and which has an orthogonal intersection in this place. I mean, that's a reason basically it's impossible to upgrade this even further in D module. That's basically probably would just be a wrong statement. But anyway, I just want to say it's a very important, to me at least, actually myself, all my group, LL, these are leading one group, and also all our students. Actually, we all bothered by this for more than 10 years, but we cannot really go any step further. Yeah, there's some very even philosophical issue has to be resolved first. Yeah, so I didn't do that last time.
So locally, it's a product.
Yeah, locally it's a product. The MS bar is the moduli space of S bar.
X bar?
Yeah, S bar is a singular Calabi-Yau with ordinary double points. But we know, as I said, the Bogomolov-Tian total theory still holds for this singular variety. So the moduli space is still smooth.
Sure.
Yeah. So when you go out, it's just the same as this one. So it's just a local compactification, partial compactification of it. Yeah.
But the moduli M bar is identified with M y.
No, the Y is just an image. I should say, I identify this. This content, let's call this pi. Then that contains the my. But this my is isomorphic to it. Yeah, because this is this again is a basic result in birational geometry. So if you have a extremal contraction in 3 volts, then the extremal contraction will deform in any flat families. So that's a reason. Once you have one contraction from Y to S bar, once you have that, then once you deform in the moduli, then that deform the contraction always. So locally you get this the whole embedding of your my as a strata. This S bar, sorry, this MS bar is everywhere, and this axis is my. Yeah, that's a picture. Okay, so instead of as I said, that's something should be understood. So I did something different. So first, I have this so-called linked B model. And I also have this linked A model. And this linked B model is on Y. And this is on X. And linked means it's you link your original B model, which is deformation theory, by those curves to be contracted. So that means you just remove them. And you study the deformation of this open space. And if you do that, then you will figure out that the deformation, the first order deformation is still this. But this thing is a little bit larger. And it's actually obstructed. Not all the directions can be integrated. And those directions can be integrated are exactly the original direction. So this includes the H1y, Ty. And these are exactly the integrable direction. And the remaining direction will actually exactly tell you, will descend to here and give you the tangent direction. But those parts are obstructed. You cannot deform it. You cannot deform it in a sense of algebraic varieties. But the only thing you can do is, once you decide to close up the variety by adding the vanishing sphere. So that's what the game plays. So you subtract this rational curves, and you deform this open space. Then you fill in the part by vanishing 3 sphere. Then you can deform. Then the obstruction disappears. Then you can deform out. So that's why it's spread. So I call this a link B model. And the good thing is, as I said last time, once you develop the correct nilpolar orbit theory, and you extend this Brown-Griffiths contact manifold terminology, this correspondence, then you integrate the maximal context slice, then you get the downstairs Calabi-Yau modular space. That's what I said last time. But the problem is, of course, in general, we don't. I mean, you unless you know how to calculate this in any effective way. But usually, when you work on algebraic geometry, you just pretend you know how to calculate. So in my point of view is there are still something need to be understood in this process. Or even though usually people working on complex geometry will not make any questions like that. They will assume then this is done. But if you translate this into Gromov-Witten, then you will definitely then you will not think in that way. You immediately feel that something different. Because what's link A model? The same thing. That means you link by the vanishing sphere, the vanishing cycles. That means you consider only those curves which could not touch the vanishing cycle. And as I said, a priori this is not defined, because nobody knows how to define a Gromov-Witten theory on that kind of open space. But since this happened in this degenerative neighborhood of this boundary point, then it turns out you can apply the cycle form of degeneration formula of Junli. You study it, then you figure out you really can define that. That can be defined. And once you define that, then we just see this simple formula. And that will recover beta. So if you want to calculate, you want to understand this, then it's very easy. You just sum over all the upper curves, the Gromov-Witten of its curve class gamma, and this is finite sum. Okay, so this part is easy, as I said. It was known more than 30 years. But the difficult part is you want to recover this. You only know this. This is A model, the original A model. But you want to understand the A model of Y. Then the link invariance simply tell you, okay, you define the linking invariant gamma of X. And this gamma is a class of the second homology of this space. I call this space W. Then I just say this is well defined. And once you define it, then the theorem just tell you these two are the same. So that's part of the construction of the link Gromov-Witten by the cycle form of a degeneration formula. So, but then you of course will ask. At least that's a problem Junli asked me when I show him this. Then he just asked, do you know how to calculate this? Okay, that's a problem. So what I want to say is, if you are working on Gromov-Witten, I mean the A side, everyone will ask you this. But if you are working on complex geometry like this one, nobody will ask you how to calculate that, because they don't care. but if you are working on A side, then everyone will be curious how could that be possibly calculated. So the job today is I will try to tell you what kind of approach can we make on that. So it's effective calculation. And this is joint work with Zhongru. Okay, and then you might ask why we join together to work on that. Okay, I will tell you why. This is highly related to his PhD thesis. Was done 10 years ago, and actually supervised by Hui Wen. Because I will show you an explicit model about this degeneration. So basically, a G24, the Grassmannian G24 degeneration. Everybody knows this can be degenerate to a torical variety. And you take this Crippen resolution, partial resolution to it. And you start with a Calabi-Yau X here, then you can end up with some Calabi-Yau Y here. And this is a beautiful carnival transition with 4 ordinary double points. And in Zhongru's paper with Lin 10 years ago, actually his thesis, part of his thesis, he demonstrated how can you. So you see, if you look at the B model, this thing has a larger B model than Y. So the job is how can you use just the B model of Y and the rational curve information to determine the B model of X. Instead of go through what I say, this is a non-effectively computable machine. And the good thing is, here you have GKZ system. And here you have this tautological system due to Bangliang and Yao. There's alpha 0, alpha 1, and alpha mu plus 1 to alpha h21, and beta 1 to beta 2h plus 1, and beta 0. That's a symplectic basis. Yeah, and we purposely choose the first mu terms to be a basis of the Lagrangian cycle. So here, gamma j from 1 to mu is a basis of V, of the Lagrangian cycle space, and with a property such that the dual basis is given by minus aij, and Poincare dual of Si. And okay, so I have this basis. Then I have the and the reason you can get this exactly this is exactly because of the basic exact sequence. You need to go back to check those numbers. So the basic exact sequence shows that you can make such a choice. Okay, so it's quite readable because you only have mu of them, but you have k of these spheres. So you should rearrange in some way like this. But the point is the coefficients is the relation of the upper stair rational curves. It's not some data on. Mu, T mu. And this is part of the relation vector, one coordinate of it. And that will define a linear function. And then this defines a hypersurface. Di is a hypersurface defined by Wi. And inside, in delta mu. And of course, you can cross this axis my to get the hypersurface. Okay. slightly more general than this data. So this is our data. But we can do an abstract version of it. So consider a degeneration of hard structure over something like this. And Ti be the monodromy around. So I assume this is contain a discrete locus. Is a hyperplane arrangement with axis. Yeah. And with k component. And then the monodromy along di assumed to be quasi-important. Degree mi. And then we take the mi. Of course, it's now log of Ti raised to the power n I. And then take log and divide by n. I just try to make it more general. But in our case, mi is true, which is 1. Okay? The most important assumption is assume the monodromy group generated by all this Ti is abelian. That's the assumption. Then you have the period map. That's a period domain. The quotient is monodromy group. That's the following code. So that's called the coordinate here T and here S, just as we did last time. Then the period map Ts turns out will be exponential of I from 1 to k and 2 pi I, and this is mi log wi and ni. And times some holomorphic function. And this is holomorphic and horizontal. Okay, that's the statement. So in a normal crossing situation, that's exactly your bottom OBC. And wi is a linear function that I just defined somewhere here. Okay. And the vanishing locus is exactly the discriminant. Okay, now that's proof. Since I think this is a mini course, I have to be over at least one proof. So that's proof. Okay. Induction. On mu. And for a case mu equal 1 is the original bottom orbit theorem of Chin-Lung. Okay, so that's the higher case. Okay, so for exponential this guy. I don't want to copy it. Just this one to your original PR. And originally, this only lived in the compatible because it multiplies some element. So it goes to maybe it destroys the polarization condition. But then you want to prove this is horizontal and holomorphic. And then, okay. So we want to extend this. We want to extend this over the discriminant locus. And you take a point. If it's not in the axis, then we can find a neighborhood UP, a neighborhood of P, such that extension to UP is achieved by induction. Okay, it's very, very trivial. So because you once you have that, I take a point. If it's not in the axis, so outside everywhere I will already have the extension by induction. So the whole point is what happens when P is on the axis. Okay. So now I rearrange this side into two parts. The first one is exponential. Now I want to write down this. It's a linear function of Wi evaluated at P is 0. And another one, of course, is non-zero. This is another exponential on the side. And this is Wi. Sorry. This is non-zero. Yeah, and then the remaining thing is completely the same. Okay. The only place non-trivial in the proof is this state. Because I have a several matrices, take this exponential. Okay. The only way I can separate this into two parts is the monodromy has to be commuted. The matrix has to commute with each other. So it requires Ni. So if this is not true, then this state is wrong. Then you apply to the B. Then we take R is the coordinate RS, where R is at least one of two. So we take away some part of the somehow this. And then there exists a unique holomorphic extension to the whole space simply by Hartle extension. Okay, so you see the proof is quite true. so that's a strange part of Hartle extension. Okay. So the only thing you need now is the commutativity of the monodromy. And let's investigate why is that true in our case. And of course, that's very easy because we have disjoint spheres. And those spheres are S3. The normal bundle is just any relative speed is 0.
So in induction, you're doing induction on K, right? Not B.
No, I'm induction
Because you have you first want to reduce the classical case, and that means you have a normal forcing situation.
well, maybe but in a paper I write on you. Anyway, that's induction can be easily handled if you reduce the situation. So the thing is, any SI times SJ, this is 0. No matter whether I equal 0 or not. But this implies, of course this is implied that I am negative. Okay, so that's done. So we have this extension. And as a consequence of this, that implies the current, which I also wrote down last time. The key point is you want to know this theta j t, which is defined to be the period integral of your A cycle, of your balancing cycle, that omega t can be used as transversal coordinate with moduli space. So of course, this is trivial for the smooth point. So the A cycle always gives you the coordinate. Now what I say is I want to look at if that could be coordinated exactly at the discriminant locus. So I claim that's still true from J and the reason we can have this correlate is because we really know what's the expansion of omega t. I wrote it down last time, but now we can write it down again. Because that's given by the Neapolitan orbit theory. So this omega t is exactly given by A0 S 2. And the reason is just is exactly the Neapolitan orbit theory, because this how can you do it? It's just you apply the exponential thing and to this ARS, and this ARS is just a vector of your V RS when you take the Hodge component degree 3 part, and you take a vector representative and multiply it, you get homomorphic 3. But you expand everything out. Then this exponential thing a priori is a huge matrix. But since all the matrix Nij basically actually not just compute. Actually, for any single one, and the total of this potency is 2. So you will just get one Ni left. Here, you not just get this. Actually, you get because of balance. So when you expand these things out, you will just get one monodromy left. Then the reason you get this form is because I choose my basis to satisfy this project. But anyway, you have to go to check it in detail. I just want to emphasize the reason I can achieve this is because of the. So now I want to go back to the link A side. So this. And the trouble is we simply don't have anything like that in A model. Okay, so of course, you think about that, then you will say, okay, what's this photon theory? Isn't that just given out J function? That looks completely the same thing. Of course, because that's a fundamental solution for the system. But if you think that way, then of course, then you cannot do anything. Because it's basically just a definition. And you write down this the exponential part, that's the monodromy. The monodromy thing in I function or J function formulation is just cohomology class there. So the monodromy is just a cohomology multiplication. Okay, that's just very usual understanding on this J function. And then of course, we don't know how to prove this kind of thing for J function when it's degenerate limit. I mean, if you can do that, then that would be in some sense that would be the best structure we should expect for A model relation R structure. Yeah, but it doesn't seem to have that kind of thing. At least I don't know. And Sean is not here. Why is it not in my talk? But anyway, that's the original PhD problem I assigned to him. so when he started PhD with me, I said, okay, your job is to develop this kind of thing. But then he came up with the type 2 transition theory. But still, this is still left quite completely open. But of course, because it's a quite different category, quite different technique. So usually, although you have this mirror symmetry idea, but if you are treating something without using mirror symmetry, I mean, for a general part, yeah, of course, you don't have any mirror symmetry. But then you have to prove it directly. But then usually you don't know how to do that. Yeah, so that's exactly the situation now. Okay, so let me tell you what's a possible way to think about this. Let's look at so I want to look at the link technology. And let's first look at local model. Pure local model. Which simply means you take your S bar, which is just a degree 2 hypersurface in P4, which is just defined by UV minus WS is T as U. So let's take this value. And this S bar is the case of T equals 0. Okay, that's a standard conical degeneration. And the text side will be a small resolution. Oh no, not small resolution. It's a blowout. Yeah, it's a small resolution. The blowout of the Bain divisor. So what's a small resolution? That means you want to blow up the Bain divisor, which is P2, defined by, in this chart, is a UW as well. And U and W are both 0. So it's just a piece of the Cartier divisor. Another piece is another one. But if you plot this one, which simply means what's the universal quotient bundle here. But this universal quotient bundle is a type 1-1 bundle. And the block is described by, the Y is defined by UW ratio is Z1, Z2, and which is also S ratio is V as defined. So you get two equations. And both equations are type 1-1. Yeah. Okay. Now, of course, the product formula plus quantum Black's hyperplane theory will imply you can take the formula of 1. Because this is product, which quantum formula is quite trivial, you know. It's a standard product, this is that. And this is hyperplane, this is dimension 5. But now you have two equations, so it's a complete intersection. So it's good you can try hyperplane theory twice. Then you can take the formula of 1. Everything is perfect. But of course, you don't have to do that because everybody knows this Y is nothing but O minus 1, the 2 power. Yeah, because you draw up a curve, you get a minus 1 curve compared value. Yeah, so that's the local model of the small resolution, the most well-studied model. So you can calculate it directly. We don't have to do that. But what I want to say is, how about if you can do that more generally? So for one point, you can do that, which is unnecessary. But how about if you have many points? How about if you have more points? So is it possible to do this? Then, okay, so before that, we need to understand what is really the value divisor. So when you have a RBR with ordinary points, the only way we can get a small resolution is exactly to blow up the value divisors, passing through those points. And because it's value divisor, so after we take a resolution, you will not get any divisor, just get small resolution. But where are those value divisors coming from? Okay, then let's think about it. When you say you have this vanishing speed in your in the general case, this is the local model. If you have a general case, then you have a relation here. And B model, so we call this a PIL. So for each error from 1 to mu, you have the mu, or not 1 to rho, you have the rho relations. You get mu linearly independent 1. But anyway, the relation supposes this. And this is I from 1 to 3. Which simply means it's bounded by a 4-dimensional real chain. This is 4-dimensional real chain, which is not a cycle. Okay, that's the meaning of the relation. But this depends on the parameter t. If you have y to x and deform to xt here, that's a degeneration, so you have this t. But t is not 0. we assume that of things to be 0. Right? So when you discuss parabial tree, you purposely restrict yourself to SU3 manifolds. So you exclude other cases. So to reduce all the topology as much as possible. But that means that will force this 4-dimensional real cycle to be have only one archetype. No, although it's just a check. But when you take, so what's WL? It's nothing but limit. So when you take P equals 0, this suddenly becomes a cycle. And this suddenly becomes the thing you want. So this is the radicalized. It's a holomorphic cycle. Yeah, in a single cycle. Okay, so we have those things. Then let's start to think about how can such kind of thing be possible. So on the level of spaces, you look at this diagram, and you have some curves here. Okay. Then it looks like, look at this one. We look at this map. And this looks like to be a fiber. So I want to view this as a topological vibration. And which looks quite strange to say it that way, because it's obviously not a vibration, it's a blow up. But in old days, I mean in 60s, if you study those kind of topological theory and higher dimensional manifolds, then we learn something. One theory which is very interesting says that any map is a vibration up to homotopy. That's one of the most striking results in higher dimensional. And it's a very important thing. So any map is a homotopy equivalent to a vibration. So when I write this map, I actually think this is a vibration in some way. But you believe or not, let me just pretend you can try something like this. So expect a quantum record of the ball. So you want to compute homomorphism of Y. What does that mean? That means you want to compute some kind of I function of it. By definition, that just means some element in the D module. So what's IY? It's just the JY multiplied by some differential operator. But this differential operator has to be started with 1. Yeah. So in the language of Lagrangian code, that just means it moves somewhere in Lagrangian code. And so that you can reverse the direction. And the reverse direction is of course called the generalized linear transform. By the way, naively you just have to take anything, any representative like this. But you suspect, is that possible? Since you want to treat this as a vibration, so is that possible? Let's write something like this. If you want to take some curve class gamma, and let's try something like beta. And of course, this is gamma not beta. And then times some kind of relative vector. Okay, so the thing about in all the theories we learn from homomorphism, it's always like that. So you always want to do some hypergeometric modification of something you already know, either from hyperplane theory geometry, the correction is only some rationally defined vibration or some rationally defined space. And then when you do localization, you figure out the wave will just behave like hypergeometric vectors. So we believe, or we are searching for some kind of this relative hypergeometric vector. We want to do that. And if you can really have something like that, then I usually call this as a quantum derivative formula. The reason is you already have some base quantum differential equation. And once you have this vector, then you calculate the differential operator associated with this one. And since it looks like a hypergeometric vector, so what you get will be a hypergeometric equation. But the hypergeometric equation could be coupled with other classes or coupled with other variables. So this vector could be quite hard. But something like this, if you expect this to be true, then that would be great. So I will call this a quantum derivative type statement. Okay, then let's try to make this slightly more precise in the following way. So Y is a blow-up of S bar along very devices. Let's say W1 to W0. Because I have the relative decay is low. So you need to blow up row of times very devices. But usually you just have to blow it up. Now that's already hard enough. Yeah. Then in each step, you set up this bundle, which is O minus D1, there is some O minus D2, and subject to some ideal shape of Z. Z is defined to be D1 intersection D2, and which is supposed to contain the Bay devices you blow up, and together with maybe some other things. So maybe some other points, curves, points. You see, the thing is, just look at the local model view. So you have a cone, and you pick out some P1 here, but you want to complete this Bay device into global Cartier devices. So here, D1, D2 are Cartier extension of W to S bar. And you can have at least two ways to extend it. And if you are a local model, then the intersection will be exactly W. Then the picture will be perfect. In the case of local model, you just get this. But if you are in global model, then you don't know, because you have this great device here, and you extend it to the picture is of course wrong, but so how can I write it? Anyway, what I want to say is you have a very device, but you have two different Cartier extensions. But when you extend to the further part, then of course the two devices can intersect. So the D1 and D2 will intersect maybe at some curves, at some points. And what I want to say is, if they intersect at points, that doesn't seem to be possible because those two are devices. But in any case, if there are points, you don't have to worry about it. Because of blow-up of points is easy. We all know how to treat it. Just due to Gassman and all this. So this is okay. But this is harder. Okay, but let's pretend you have this picture. Then let's take Y Basically, that's the definition of block. But since you have this this diagram, so this will embed into the product of a symmetric power of but this is by definition a vector bundle, the original vector bundle, the projective bundle. So so you can realize it just as in the local model case, it's a subvariety in the vector bundle. And if you are really lucky, such that you still get a complete intersection, then you are done. Yeah, but as I said, usually you cannot expect that. And even worse, the really difficult problem is the following. The first one is, of course, the formal return on S bar is not blocked. The formal return invariance on singular space is only, as far as I know, is only defined for the Riemann state, for OB, for Cauchy singularity. If you really have a hypersurface singularity just like OBP, no, there is no definition. Actually, you don't know what's, you can try to define it, but then it's almost unsure if your definition is okay. The reason is, if you believe formal return invariance should be deformation invariant, then somehow you should fear the formal return invariance of S bar is formal return of X, because that's a smoothing. But however, if you believe in prefirm resolution conjecture, then you sort of believe your formal return S bar should be formal return of Y. So that's why. But you know that those two formal return are different. So I already tell you, depending on which group you belong to, usually you will choose the wrong definition because they are completely inconsistent. So the deformation invariance and the prefirm resolution are definitely contradictory to each other. But why people didn't observe that? Because all the people working on this in this area always try to do the setup so that there is no transition. So either, for example, in the standard series of prefirm resolution conjecture raised by Ron long time ago, 25 years ago, always he treat this Cauchy singularities and he work on this step. I mean Chin-Lung cohomology, and then he work on this orbital cohomology. But once you have that kind of singularity by the Schrödinger theory, those singularities are rigid. There is no smoothing of that singularity. I mean, you just take the simply possible, the C3 model any SL3C finite group, and if you are in isolated singularity, no, then there is no smoothing. So once you work on that, of course you will not see this, and of course that should explain why the formal return here should be the formal return here, because you don't have any excess B model. And on the other hand, if you work on one kind of singularity which does not admit any prefirm resolution, for example, you degenerate your variety to one order double point. If you just degenerate to one order, then you know by Friedman's criterion, no, you cannot have any small resolution. So in that case, of course, since you don't have any this other side, then the formal return should be invariant on in the bottom. So I just thought about this problem for a long time, and yeah, of course, it's my version to explain this. I think the A plus B theory is still the only possible consistent theory so far I can imagine. Because I have to believe during this kind of transition, part of A model will be transformed to part of B model and vice versa. And we should really find a way to control it. Okay, that's the plan. The reason I talk about this. But anyway, that's a big problem. It's undefined. And the second one is, I just must say, D1 intersect D2 might have as I said, if it's just point, that's equity dependent. But if you have a curve, then that means we need blow-up formula over curve. But we know so far there is no general blow-up formula on convolution theory, even around curve. So of course, there are many kind of blow-up formula in convolution theory. And usually the formulation is the following. So in terms of D module, that's the first type of blow-up formula. Second type is in terms of Lagrangian cone, but that's the same formulation once you understand what's the given Lagrangian cone. And then why is not a truly satisfactory blow-up formula? Because what we really want is I want to know how to calculate the convolution variance from one to the other. But if you allow yourself to move in some uncomputable shift on the Lagrangian cone, that would be basically the problem. So, but if you really can allow that, then I can try to formulate something for you here. So that the thing is the following. Actually, it's partly suggested by Zhong. So okay. So probably this thing, since it doesn't exist, so the JS bar should be replaced by some PJX for certain differential operator starting from 1. And maybe even this I'm not so sure. But let's say it's some choice in the Lagrangian cone. And to say this, then simply says that it's an I function. And then that reduces the problem to in a very similar situation in the type 2 transition. So you go back to think about what Susan explained this morning in the type 2 transition. Why we can do anything, the comparison of convolution, is because we exactly avoid the singular space S bar. We create something called the canonical local B model. And that canonical local B model will directly embed the space you want to compare, the y and x, into something else. And the something else is every term can be computed by a known tool in convolution theory, like split quadratic bundle, like hypervector bundle or sections, all those kind of things. So what's the candidate for this P? And according to what I just described, so the picture is both E and P. So this vector bundle and this P depends on the very divisors. Okay, that's the proposal. So it does not depend just on local information. Okay, so for example, let's do one test like this. So you detect a variety. Just trivial. You take a curve, just P1. And you look at the normal bundle. You know that. And then you take two curves, are both P1. And the normal bundles are exactly the same, isomorphic. Then you do blow up on this curve and that curve, on the same space. You get two blow up. Then ask yourself if the quantum cohomology are the same. And the answer is no, they are not the same. Because the convolution theory, it really detects something further. So they are not the same. And this is even worse for blow up with singularities, like Bay devices. So what I want to explain is there is no then it's possible. Okay, and if you want to see a little bit more about the details, you can check. I have an article in Stream Math, 2015. There is one section to describe this blow-up formula as well as this vectorizing. I only wrote very briefly on that, but there are some more formulas, more precise than this, and you can get some information on that. Okay, so I only have a few minutes left, so I just want to show you one example, just calculated by Zhonglu. He actually calculated this for me yesterday. Because I just asked him, since you can do the B model test, why not do the A model test? Then he has to calculate some Chicago equation. So let me do that for you. So essentially the example is G24 and degenerate G24, and then you resolve the toric G24. And you have S bar here, right? And here is X. And this is actually a twofold completing the section in P5 by the following two equations. The 2 is just the proper invariant. So P12, P34 minus P13, P24 plus P14, P23 equals 0. This is a quadrant. So the Grassmannian is embedded inside the projective space P5 as a quadrant. By this equation. But then you can do a deformation simply by adding a parameter T here. So if you set T equals 0, then of course you just get two terms. Then that's the definition of toric variety. So when you set T equals 0, you go to toric variety, T24. And it's singular, so if there's a result, there's PQ24. And since you have another degree 4 equation, because you need to fit this 6, so you need degree 4. So the total pursuit degree is n. But then, when you want to know how many ordered out points you have, look at this equation. Each point gives you degree 2. So you should get just 4 ODPs on S bar. So when you take T equals 0, you get S bar. Okay, so that's the standard degeneration. Understand? You have 4 ordered out points. And then you resolve it to get this y. And you calculate the Picaboo's equation. You have Lx, which is theta 1 squared, theta 1 minus theta 2, squared minus x, k 1 to 4, then 4 theta 1 plus k. And another one is y. So my variable here is x is v1, so corresponds to theta 1, which is x multiplied by x. And y is v2, which corresponds to theta 2, which is y multiplied by y, as usual. The equation becomes theta 2 minus y, theta 1 minus theta 2 squared. That's the Picaboo system. And this is a famous example of, you see, this is become number 1. And this is become number 2. So here you can compare relative to what? Am I right? Okay. But look at this. So so you want to calculate Of course, y is the B model content variable. So you want to restrict this. And this one is very crucial. But anyway, I don't have time to explain it. So it's 1. And if you do that, eventually what you get is this operator Lx, which is a very tricky operator. But you restrict to y equal 1. That will give something. Theta 1 to the 4th power minus this. No, I'm doing something wrong. Okay, sorry. Yeah, I'm doing something right. So, how I can write down this? This is Picard number 2. So I'm calculating the Picard-Fuchs equation on this toric model. I get this 2. But I want to recover the Picard-Fuchs equation here. Okay, so I do a restriction to this. So this y is extremal variable. It's QL in the previous notation. So I want to restrict this to be 1. This is hybrid geometry, so we know that will go to 1 instead of the spatial value. But anyway, it's a hybrid geometry, so it's okay. Let's go to 1. So we do this restriction, and we get this. And it's justified. It really is a Picard-Fuchs equation for this model. Okay, so this is okay. Check. It's true for complete the second result. But that's not our purpose. Our purpose is to look at this one. So the point is the following. For this Picard-Fuchs system, of course we can reconstruct this Picard-Fuchs system here. If you think about B model, then this is actually quite trivial. It's just a monodromy invariant system. You do a B model, that's that. But in the A model, you can still do this B module computation. This is not a trivial computation because you cannot just let y equal 1 and substitute into it. That's wrong. Because you need to do some B module. This non-commutative algorithm. But anyway, once you do that, the A plus B program is the reverse one. So suppose you have this, given this, and Ly. So the condition is, you already have the downstairs thing. Of course, you know that one. But you also have the extremal rate contraction, which is governed by this Picard-Fuchs equation. But this Picard-Fuchs equation is twisted by the different variable. It's coupled by the x variable. It's very different from type 2. You still remember the last talk on type 2. That Picard-Fuchs equation, even though originally it's very complicated, it's a 3-order differential equation. But after you do the mirror map, you suddenly figure out the mirror map is only one variable. It becomes a Zagier ODE, which is second order. And even though it's not really necessary to be hybrid geometry, it still can be controlled by module 4. But in this case, you get something better. You are already Picard-Fuchs, the hybrid geometry. But you get something worse. You have a coupled direction. Okay, so then the whole problem is just, if you start with this and this, you can still reconstruct the system. It's okay. You still can get this idea. And the reality is, you just do this compatibility check. So you start to commute these two operators. And of course, it's not commuted, otherwise it's a system. So it's not commuted, so you start to add some correction. And after some work, you know you can do that. So this part is okay by D module method. So what's the remaining problem? The only one problem remains. How do you know this something like Jx bar times relative. I want to have this kind of thing to be a candidate of that. I say I want to design this. But it's equivalent, it's basically equivalent to design this. Because this is Ishmael operator. So that will detect the Heavy geometry, the relative heavy geometry factor. So the plan is the coupling should be determined by the information on their devices. And actually, we tried all examples we can try. We can get that. But unfortunately, we don't have a uniform description. So we don't have. In all examples, we try all the continuous example, XA, all your example, all these two parameter examples, and also the Grassmanning examples. Most examples we try, the velocity is okay, but we don't have a really uniform description without any global knowledge of the model. So, and that's the finish of the A plus B program. So, so the A. To put in the most easy, simplest explain way is to decide this extremal hypergeometric couple system, and to decide this twisted factor using the big device. Thank you.
Thank you very much. Are there any questions, comments?
Just one simple question. The simplification is for the I function, not the deformation family, right?
This decoupled system is now used as to calculate the A model.
A models.
But you can, of course, not calculate the mirror B model.
Yeah.
So usually people work on this,
Yeah.
especially in your example for the two parameter model of Candelas. You are making use of this. This is become number 2. So when you do mirror, you get a two parameter B model diamond. And in that case, of course, this decoupled will calculate the Gauss-Manning connection. So the picture is the same.
And from the B side, if you look at the specialization y equal 1.
Yeah.
Is that true? That's from if you look at the from
Yes, that's exactly.
the screen and
Yes, that's exactly. So actually, because I don't have time. Otherwise, if you calculate exactly the same calculation for Candela's XA example, and then you see the discrete locus is something like this. I forgot, not completely. But anyway, there's so-called one carnival point. That one is a dead end. So you don't have any small resolution. Because there is only one ODP. But there is a component called C1, and which corresponds in Candela's coordinate is this group is 1. And he says that singularity is some isolated multi-nasty singularity. He said that, but that's wrong. The statement is wrong. It's not isolated singularity. It's actually some higher dimensional component. But he's also right, in a sense, if you think as a Berlin-Mumble stack. So because of all the higher singularities, actually they are V2 quotient axes. So if you do think as a stack, then there is actually only one isolated singularity. So if you work on that model, actually I spent a lot of time working on that model to make sense of all of this. But in that case, the specialization Q, this Q equal 1, is exactly the specialization for this locus. In his notation is something called this one, or something called something like this, and this one. So some confusion like this. And if you look at that example, it's even more interesting. Because of the mirror of that is actually a type 3 contraction of genus 3 curve.
Yeah.
So if you deform it, you still get ordinary double point. So very similar to this example taken by Zhong. But the difference is, in the XSM model, you can really deform the transition so that it becomes 4 ordinary double point.
to split it into 4 ordered double point. So that disproved the conjecture of Morrison. So in old days, Morrison conjecture, he made a lot of conjecture and improved the conjecture very good. So the very original conjecture is where I was a student. So he said, okay, a canonical transition has a mirror transition to be a canonical transition. Then of course that's wrong. Has a lot of counter examples. But it's very difficult to formulate this conjecture. For example, the one I just explained about SA model. You have type 3 transition. And in that, transition, you can deform 4 ordered double point type 1. But if you look at the mirror side, it's not a primitive transition. Actually, if you want to resolve this singularity, the only way is to block this, block this, and block this. And do the 3 block, you resolve the singularity immediately. So that's a relative Picard number 3. So it's not primitive, but it's a relative Picard number 3. And we check. I can do some local deformation to split the point to 4 ordered double point. But since there is no global projective resolution or smoothing of that. So in that sense, the naive Morrison conjecture is also wrong. And I think in your talk you described this ocular tone and the tone with boundary. I think one of the really important questions to ask about global mirror symmetry is really to compare the behavior of the B model and the A model on the boundary. Because that's the thing I'm doing. Yeah, and the answer is quite unclear. Yeah, it seems to be more complicated than we previously believed.
Any other questions, comments? That question actually, I'm interested in how you find the B divisor. It comes from relation of.
It's just ordered double point. So you look at the local model. So if you blow it up, blow up the point, then that's not prepared. Because you create a divisor. So it's not a prepared solution. So in old days, in minimum model theory, like the work of Kamada, Kola, Mori, so they all know you need to do some small resolution. But then you should block, so then they found the prepared divisor. Yeah, so they found, okay, you need to block divisor. But the divisor, if you block divisor, you block nothing if it's Cartier. So the only thing can change is the non-Cartier locus. That's the break. So that's just it.
Is it obvious that the chain can be taken algebraically?
Oh, no, that's as I said. Since you restrict the topological, because you restrict your topology, you restrict everything like this. So you look at your Hodge diamond. Everything is 0 except the algebraic cycle one. Yeah, so that cycle can be taken to be algebraic. Of course, you can take that to be trivial, but you can deform that to be algebraic. That's because you purposely do it for SU3 algebra.
Any other questions, comments? If not, let's thank the speaker again. What time shall we start the next? Okay, maybe we can start at 3.
Okay.
Okay.